Okay.
Hello, everyone. Thank you for joining today's GeoScience and GeoEnergy webinar. We are pleased, myself and Sebastian Geiger, my friend and colleague at Heriot-Watt University in Scotland, to host you this week also with yet another exciting geoscientific and geoenergetic talk today. We are also especially grateful and thankful to all the keynote speakers who have graciously accepted our invitation to present their research and share their knowledge and experiences with us, and also help us to combat work from home isolation. Please do subscribe to our channel so to get the access to the archive and also get notifications and set reminders for the upcoming ones. We would like to also, both Sebastian and myself, remind you about the Tea Time Talk series, which is run by mostly junior researchers for you all, including especially junior researchers who can volunteer to share their work, research findings with others, and especially practice on establishing their network at early stage of their career. Without further ado, I would like to introduce you and introduce all of you and you actually to Joshua White, our keynote speaker of this week. We are pleased and honored to have him this week with us. Thanks a lot, especially he's up quite early in California. Last week we had also another guest from California. We are going to stay there until they wake up quite early, and then we come back to Europe. So it's our pleasure again to host you, Josh. Thanks a lot for accepting our invitation. I'll read a few lines about him and then the talk will start. Josh is a research scientist at Lawrence Livermore National Lab in the Department of Energy of the US. His research centers around using larger scale computing to improve our understanding of complex geologic systems, with a particular focus on geologic carbon storage and induced seismicity, quite hot topics also in Europe and worldwide. He received his Bachelor of Science degree in Civil and Environmental Engineering from Princeton University, and then moves to California, where he did his master's and PhD in Civil Engineering, Civil and Environmental Engineering, Department of Stanford University. He joined Lawrence Livermore National Lab in 2009, and he still is there. At the beginning, he was a postdoc fellow, and now serves as the group lead for the subsurface flow and transport group in the lab. He is a member of the editorial boards of the International Journal of Numerical and Analytical Methods in Geomechanics and Acta Geotechnica. He's also the Induced Seismicity Working Group lead for the US Department of Energy's National Risk Assessment Partnership. Please do visit his page and study his very comprehensive and useful publications. I can say I am one of those who actually reads his papers with a lot of interest. Do search and you will find a lot about him. The time limit doesn't allow us go further beyond. It's a pleasure to have you, Josh, with us. Thank you again for accepting our invitation to give a talk. To the audience, please note, Josh, lecture will last for about 30 minutes and then followed by discussions. And like before, please type in text your questions. Sebastian will chair the discussion session after the talk. Please do not wait until the end of the talk. Whenever you feel appropriate, please do type your questions. They may trigger other questions also. So without any further ado, the stage bandwidth, the screen is all yours, Josh. Thanks once more, please.
First of all, thank you again, Hadi, Sebastian. This is it's an honor to participate in this series. There have been many challenges with the COVID crisis, but there's been a few bright spots, and one of them is the innovative ways we've been coming together. And so I think this is a nice example of that. The second thing I want to emphasize is that I have the pleasure of working with a large group of collaborators, many brilliant people at Lawrence Livermore and many other institutions. And so everything I'm going to talk about today is actually joint work. I just have the pleasure of being a spokesman for a lot of brilliant people. So So today I thought we could talk about geomechanics and computational geomechanics, how we actually simulate these processes. I think that they're very important for many subsurface systems, so a lot of the work we do is related to CO2 sequestration, geothermal energy, oil and gas, these sorts of things. To set the stage here, I have a cartoon of a CO2 storage system just as an illustration. Here you can imagine that there is some point source of CO2, which we might transport by pipeline to an injection well, and then inject it deep underground into a subsurface reservoir. And then within the system, there's all sorts of geomechanical interactions that we might be interested in. If we look at the well itself, as we're drilling the well, there's lots of concerns about wellbore stability, how we choose mud weights and so forth to guarantee a nice stable hole. Once the well is constructed, then the integrity of the well could, in principle, depend on the stress conditions around that well. As we inject fluids in the subsurface, we can potentially build up substantial pressures, substantially perturb the stress state in the reservoir and in the surrounding rock. Many reservoirs have a stress-dependent permeability, so that as we inject, we may see preferential flow in certain directions or substantial changes in the permeability response. If we inject at too high a pressure, we may actually hydraulically fracture the rock or cause shearing on pre-existing fractures. At a larger scale, if there are existing faults, we may change the effective traction acting on that fault and potentially cause it to slip. And it could do that in a quasi-static way or in a dynamic way, leading to induced seismicity. And in a worst case scenario, that could actually create new leakage pathways, maybe out of the reservoir. And then more interestingly is these deformations that we might induce actually propagate quite far, well away from the injection point. And so there's been a lot of interest recently in using direct deformation measurements as a monitoring technology. And so, at the surface, we may deploy tilt meters or INSAR. You may imagine running fiber optic cables down a well and doing distributed strain sensing and so forth. So to give you maybe a nice illustration of this, this is the Insala CCS site. So if you're not familiar, Insala was one of the first large-scale commercial onshore CO2 storage projects. It took place in central Algeria between 2004 and 2011. And so Insala is located at a gas field. And so on the left, you can actually see this gray region is a sort of a map view of the gas cap. And there are many production wells that were producing gas from that gas resource. That natural gas had a very high CO2 content. And so the operators would remove the CO2 and then re-inject the concentrated CO2 in 3 wells on the water limbs of the structure. And so these are wells KB 501, 502, and 503. And what's interesting about Insala is that they deployed a very comprehensive monitoring suite, one of which was actually satellite-based surface deformation monitoring. So they used a technology called INSAR, which allows for quite high resolution monitoring of uplift and deformation at the surface. And that's what we're actually seeing here in the right figure. So this is labeled range change, which is the movement of the surface towards or away from the satellite. The satellite's not looking perfectly vertically down, so it's not quite vertical uplift, but close enough for today's discussion. And what's interesting is you can actually see above the injectors, these KB 501, 502, and 503, as fluid was injected and the reservoir itself began to inflate, we can actually see substantial uplift at the surface on the order of about 2.5 centimeters. Now, the geomechanical behavior of Insala, it's an interesting story. It's very complicated. And there's not time to really go into it today. But one thing I think you can immediately see from this figure, in fact, is that it's clear that there was a very strong interaction between the fluid flow and the in situ stress state. So in the upper right corner there, I've labeled SH max. This is the orientation of the maximum principal in situ stress. And you can actually see that the deformation plumes are not circular. They're kind of elliptical, and they're strongly oriented in this SH max direction. And there's a variety of explanations for that. But we know, for example, that Insala is a fractured reservoir. And so there are strong interactions between the fluid pressure, the fractures, the permeability of the system. And so there is this sort of preferential migration of fluids in this northwest-southeast direction. So much of our work is focused on the deep subsurface, but I do think it is important to recognize that there are many shallow sort of geotechnical applications for which geomechanics and coupled processes are extremely important. So for example, for many years, I've had an interest in rainfall-triggered landslides. These are a very destructive hazard in many places around the world. And you can imagine as if you have a hillside and a soil and very heavy rainfall, that water will infiltrate into the pore space, change the saturation, change the effective stress conditions, and actually potentially trigger slope failures. And so here we see a massive slope failure from Peru in 2018 with sort of a primary headscarp, a primary failure surface. And then once that was initiated, the whole mass broke up in a quite complicated pattern, and actually slid. Here you can see there's some houses in the lower right corner. Okay, so we're interested in developing sort of computational tools that are able to model these coupled processes, and that can be used for things like hazard assessment, risk planning, and so forth. So today's talk is about HPC, high performance computing. And so I love to begin with this photo, which I just find I get a kick out of. This is Lawrence Livermore's first computer from 1953. And so it was a UNIVAC 1, and this huge toaster oven, as they called it, could perform a mind-blowing 2,000 operations per second. And if you think about it, many of you probably have a smartphone within easy reach. And it's interesting to think about the computational power that you have in your smartphone compared to a groundbreaking system like this in 1953. But if we fast forward to today, so this is the top 500 list. And if you're not familiar, the top 500 list is basically a list of the current 500 most powerful supercomputers in the world. And so right now, the number one system is in Japan at Riken. This system has 7.3 million computational cores. So it's quite impressive. Lawrence Livermore Lab, where I work, we're currently sitting at number 3 with our Sierra system that was installed in 2018. You'll see that these systems are providing performance now on the order of hundreds of petaflops. Okay. And you'll also notice that here we're looking at the top 5, and these are all sort of national laboratory and government institutions. These are big national investments in supercomputing to sort of put these computers in the top 5. But what I find very interesting is if you start to look further down the list, there's a huge number of energy companies that actually appear very high up in this top 500 ranking. And so, for example, the number 6 computer in the world is actually owned by an oil and gas company, by ENI, which is, again, it's an odd thing to think that this is not a government institution. This is a private industry that cares so much about high performance computing that they're willing to invest hundreds of millions of dollars in this technology. And as you go further down, you'll see Total is at number 15 with their Pangea 3 system. We've got Petrobras, PGS, a variety of others. Just for comparison, Facebook, we think about the technology sector as being driven by computing, but they're interested in a very different type of high performance computing. And so the first sort of standard tech company you come across here is Facebook at number 76. Now, these companies, the use case for this is largely geophysical imaging and processing of seismic data. It's very well suited to high performance computing, and it's an exciting sector to be in, thinking about the future systems and how they might impact geophysical imaging. Our work, though, in reservoir simulation, we look at this and say that these companies are investing such resources in these huge tools. Can we take advantage of them at a similar level as what's being done for geophysical imaging? So, I will also point out, just as a note, which I won't be able to talk about much today, but many of these newer systems, the performance gains are being driven by GPUs. And so this is really exciting. It holds huge promise that GPUs can dramatically accelerate many of our algorithms, particularly those that have a high level of intrinsic parallelism. It's also, though, a little terrifying in the sense that many of our codes and our algorithms that have scaled beautifully for the past 10 to 15 years will no longer work on these systems. All of a sudden, we have to revisit them and think very carefully about things that we haven't had to think quite so carefully about for many years. Memory bottlenecks, simplifying algorithms to remove branching logic and to find high levels of intrinsic parallelism, these sorts of things. That's, I think, where much of the sort of computer science and algorithmic challenge will lie over the next 5 to 10 years. So looking forward, this on the left is actually a plot of the top 500 statistics for the past sort of 20 or 30 years. We are currently in the petaflop age, but in the next few years, we're actually going to enter into the exascale age. And so the US Department of Energy, we already have a clear roadmap of the first exascale systems that will be deployed in the US. So the first one will be this Aurora system, which will come to Argonne National Lab in 2021, then a new system at Oak Ridge later, and then eventually Lawrence Livermore, we're going to get our first exascale system in 2023, and that should provide something like a peak performance of 2 exaflops. So, okay, so how do we actually use these huge computational resources? And to be honest, there are a huge number of bottlenecks. Here I'm sort of showing the diagram of our reservoir simulation and computational geomechanics workflow. We go from characterization data to constructing models. We then make decisions about the governing physics and the constitutive models that we want to use. There's questions about how best to discretize that physics. We then need to solve it using efficient algorithms. And then we need to think about how we actually program those algorithms so that there's a nice blending between algorithm and hardware, and it runs very efficiently. And all of that just gets us to sort of the forward modeling phase, whereas in reality, we often wrap that forward model in sort of a broader workflow of data assimilation, inversion, uncertainty quantification, risk assessment, with the ultimate goal of actually providing decision-making capabilities. And like I said, there's bottlenecks in each one of these circles. There are whole conferences devoted to each circle. So today I thought I would pick out one, which is, I thought I'd talk a little bit about linear solvers. I know for many students and for many people, it's the first bottleneck that people encounter. People in their PhD code up a very clever discretization of some novel physics. They try to run it, and their linear solver doesn't scale. They're using a direct solver, and so they can only run 2D problems, small 3D problems. And so it's kind of the first place where a dramatic improvement in your solver algorithm can open up the space of much larger models. And so this is one we've been working on for many years, and so I thought I'd focus on this one in depth today. And so, like I said, geomechanics, it's a very broad topic area. And so when you say that you're running a geomechanical simulation, we really need to be much more specific about, what are the equations you're solving, discretization, and so forth. And so to fix ideas a little concretely, here's one model that we use very frequently, which is multi-phase pore mechanics. Okay, so imagine that I have a sponge, a deformable rock, filled with a wetting fluid and a non-wetting fluid. So that might be oil and water or any other combination of those sorts of fluids. We end up with, to model that system, we're interested in the displacement of the rock, the wetting phase saturation, and the fluid pressure. And for simplicity here, I'm going to ignore capillary pressure so that we really just have one fluid pressure that we need to address. And so our governing system of equations, there are three balance equations. We have a momentum balance equation that relates the deformation of the rock, the stress in the rock, the self-weight and the body of forces applied to that mixture. And then we have two mass balance equations, one for each of the fluid phases. And these equations are tightly coupled in a variety of ways. For example, fluid pressure will impact porosity, and the porosity will impact the storage available for fluids. The fluid pressure will obviously also induce deformation of the rock. The displacement field has a direct control on the porosity. There are subtler couplings as well. So for example, going back to Unsala, imagine that our permeability here depended on the state of stress. That would be another source of coupling. And so in general, we end up with a nonlinear set of equations that we need to solve. And we discretize it using a certain strategy. And that's a whole topic in itself. Most frequently, we use a finite element discretization for the mechanics portion of the problem, and some sort of finite volume discretization for the fluid flow part of the problem. But there's, some people will cast the whole problem in a finite element context, a whole problem in a finite volume context. Recently, there's a lot of interest in mixed mimetic and hybrid finite volume methods, virtual element and polyhedral finite element methods. So I think the space of the strategies you might use to discretize this are quite large. But again, sorry, there's a little delay in advancing the slide. But again, on the left here, I'm showing sort of the typical structure of a nonlinear code that might solve these equations. We begin with some sort of pre-processing loop stage where we build our mesh and assign properties. The governing equations are time dependent, so we go through some time loop. We then have a nonlinear set of equations, so we need some sort of nonlinear solver. Most frequently, this is a Newton iteration, though recently we've been exploring a variety of other nonlinear solvers that might be used. Within that nonlinear solver, you have to assemble your linearized system of equations. And then we're left with a linear system of equations, ax equals b, that we need to solve. Since we use implicit time stepping for so many of these types of problems, this is where this linear, the necessity of solving a linear system is really appearing from. And so on the right there, you'll see our linear system has three types of variables. For example, we have displacements u, saturations s, and pressures p. And so if you actually look at the matrix that's being assembled, it has this sort of block structure where you can partition it into a 3x3 structure. So AUU, for example, it's a sparse matrix itself, but it represents the coupling between all the displacement degrees of freedom in the mesh and with all the other displacement degrees of freedom in the mesh. And similarly, AUP would be all the couplings between displacements and pressures in the mesh. And from a linear solver point of view, it's very important that the linear solver that you apply to that system has a good understanding of this sort of multi-physics coupling. Now, you can apply a direct solver to this system, but in order to achieve good scalability, we typically used a preconditioned iterative method. Those use much less memory. The algorithms are much more scalable. But the challenge is that the convergence of that method is very dependent on how well you precondition the system, by which we mean how well you sort of control the eigenvalues and eigenvectors of your iterative matrix, which really controls the convergence rate. And to show you how important this is, I want to show a simple example. So this is a single-phase test problem. This is Cryer's sphere. It's a classic sort of poroelastic benchmark problem, where we take a sphere, and here we've actually just taken 1/8 of the sphere. It's loaded externally by a load, but it's a elastic medium saturated with a fluid. And so as that stress is applied, fluid pressure builds up, and that's what you're actually seeing on the right, is the pressure at the center of the sphere versus time. So fluid pressure builds up, but then that fluid is able to actually drain away through the outer boundaries of the sphere, and over time that pressure relaxes. Here we've shown a comparison between the numerical model and the analytical model and two numerical solver schemes. One is what we call a fully implicit scheme, which is a monolithic scheme where we say we're going to tackle that entire matrix directly all at once. Many people in the community prefer to use what are called sequential schemes, where you may actually iterate back and forth between certain components of the problem. If done well, both will converge to the exact same solution. So they're just different strategies to get to the same answer. We tend to prefer the monolithic scheme, though, because there are a variety of ways that we can actually accelerate both the convergence and the speed of the algorithm. And so, for example, in this example, the monolithic scheme, this fully implicit scheme, actually ran 5.5 times faster than the sequential implicit scheme. So, okay, so like I said, preconditioning is essential to good performance. And so what we mean by that specifically is that we're trying to solve a linear system, AX equals B, but we don't actually work with that directly in our iteration. We pre-multiply, for example, that system by a preconditioner, which is this operator P inverse here. We multiply both sides. So obviously the solution X here hasn't changed, but the matrix that we're actually iterating with is now this P inverse A operator. And if we choose P inverse well, we can actually, again, control the eigenvalues of the matrix and really accelerate the convergence of the iterative method. And you can see this most clearly if you actually do a refinement study. And so here what I'm showing is a plot of the number of iterations to convergence. Okay, so this is a measure of how much work we have to do versus the mesh refinement level. Okay, so we start with a problem at a certain mesh refinement, and you'll see here we've used two preconditioners. And for very coarse meshes, both work very well. We can converge in less than 40 iterations. We would probably declare victory. But then if I refine the mesh, you can see that if we have a poor preconditioner, it's not as good at maintaining this control. And so the number of iteration grows to a little bit more than 60. And then if we refine it again, all of a sudden it's taking close to 100. And then if we kept going, you can imagine that our algorithm really isn't scalable. What happens if I want to run at a mesh refinement level of 5, 6, 7 on a very large supercomputer? This algorithm is not going to be able to take advantage of it. Whereas a good preconditioner, so here this fixed stress preconditioner is one, this one is able to really control the convergence rate regardless of the mesh refinement level. And so this is the first ingredient of scalability that we really need, is this sort of flat behavior or slightly growing behavior with mesh refinement level, which means that we can run very, very large problems. Now, the talk is very short today, so I won't be able to describe the methods that we actually use for doing this, this sort of preconditioning process. I'll say in recent years, we've started relying heavily on the concept of what's called multigrid reduction. So this is a flavor of algebraic multigrid, but that's very well suited to multi-physics problems. Okay, and so the boxes here are meant to represent the Jacobian matrix of your system. And remember that that fine scale Jacobian matrix has a 3x3 block structure. But what we do is in our preconditioner, we construct, like algebraic multigrid, a hierarchy of coarser and coarser problems. And the difference between sort of a standard multigrid method is that hierarchy is actually constructed using successive eliminations of the field variables. So we start with a problem that's got displacements, saturations, and pressures, U, S, and P here. We construct a coarser version of that problem. That's an approximation that eliminates the displacement fields and only includes saturation and pressure. But we try to do that in such a way that that problem has knowledge of how the displacements impact the flow problem. And then we further coarsen to a pressure-only problem. But again, that problem needs to be sparse, and so it's an approximate representation of the finer scale flow problem, but it does have knowledge of how the saturations impact the pressure fields and so forth. And then once we have this sort of hierarchy of coarser and finer problems, we use smoothing operations at each of the levels, and then restriction and interpolation between the levels to quickly damp out error components associated with each element of the problem. So I know it's a very crude description. If anyone's really interested in the algorithm, it's really best to read a paper describing it. And so this reference, Bui et al. 2020 and CISC provides a very detailed description of exactly what's going on, and I would point you there. I'll say one of the things we like about it is that it is largely algebraic in nature, in the sense that it doesn't require an invasive modification of your code, unlike many other physics-based preconditioners. We need very limited information from your code in order to construct this hierarchy. However, I will say that it's a toolkit. It's very much like a well-stocked kitchen. It provides lots of tools for doing smoothers, smart strategies for constructing this hierarchy. But at the end of the day, you do need a recipe that's specific to the problem that you want to solve in order for this to work. And so over the years, we've developed quite a few recipes that work for a broad class of problems, and we'd be happy to share those with you if you're interested in. But as we encounter new problems, we have to construct, we have to play around with new recipes. So, okay, so to show you how this performs on a few examples, this is a multi-phase pore mechanics problem. So the geometry here is a little artificial. We needed a problem that we could refine to very fine mesh levels in order to run very large models. And so we started with this kind of very simple geometry. Here you have an injection well at the top corner where that blue triangle is. And then there's a production well in the lower corner where that red triangle is. And then there's a high permeability channel that actually kind of winds in a staircase fashion from the top injector down around to the lower injector. And then in between is sandwiched a very low permeability shale, you can imagine. And so we inject a fluid, wetting phase fluid into the top injector. And so you can see from the saturation plot, this plume of the wetting phase actually migrating down to the lower injector. But as that happens, there's very strong coupling with the pressure field and the displacement. And this problem is just deliberately constructed to have very, very strong coupling. So it really exercises the quality of your coupled preconditioner. And so here we're doing what we call a weak scaling study. So we start with a problem at a certain resolution. So at the finest resolution, the problem has 680,000 degrees of freedom. This was too large to fit on one core of our machine, so we put it on 2 cores. Then what we do is we refine the mesh. And so that problem will have roughly 8 times as many degrees of freedom, but we give it 8 times as many resources. So we put it on 16 cores. And then we refine again and we refine again until eventually we have a problem with 337 million degrees of freedom on about 1,000 cores of our machine. Now, it's a nonlinear problem, and so it's a little bit difficult to do a scaling study in the sense that the number of nonlinear iterations changes a little bit as you go from one refinement level to another. But what is very clear, if you look at the GMRes iterations here, is that we have very good control on the iteration counts. We are not seeing this uncontrolled growth of iterations. And so we have a scalable algorithm. And then if you actually look at the total time, you'll see that there is some growth. So, the problem that is 512 times as large does take longer, but it only takes 3 times longer. And we're talking on the order of a few seconds to actually execute this. We also know we have very good strong scaling. And so, for example, if you're willing to put 2,000 cores or 4,000 cores, we can actually cut down this time, approximately with 100% efficiency until we put something like 50,000 degrees of freedom on each processor, at which point communication costs start to overwhelm the system. Okay, so that was one set of physics. But now imagine that we switch to a very different set of physics. And so here we're looking actually at a hydraulic fracturing benchmark. So here we have a big hunk of rock. There's a horizontal injector running through it. We pump fluid at very high pressure through multiple perforations and do a multi-stage fracturing job. And so those green, blue things are actually fractures that are growing away from the well. And so here you can see actually a sort of a head-on view of these fractures as they're growing with time. So there's and the unusual shape and the heterogeneity of the fractures is being controlled by the in situ stress conditions, which are very heterogeneous, and then also the interactions of one fracture with another. We get all sorts of stress shielding and these sorts of complicated things that lead to very complicated fracture growth. So the physics here is mechanics, it's fluid flow, but it's very different from poroelasticity, and so if we took a traditional poroelastic preconditioner and applied it to this problem, it would choke. But using this multi-grid reduction, we can actually tune the system to be well suited to this particular set of physics. And so here, for example, we're doing, again, a weak scaling study. So we start with a problem with 21 million degrees of freedom. Again, you need a certain resolution to be able to sort of intelligently solve the problem. So we have to start actually with quite a large problem. And therefore, we start with 216 cores with about 100,000 degrees of freedom per core. But then what we do is we refine and we refine until eventually we have something like 171,000 degrees of freedom. 171 million degrees of freedom. Our matrix is 171 million by 171 million at each Newton iteration of our problem. And if you look at the average number of iterations, though, you will see that they are very flat. So we take on average 30. We don't see substantial growth. And if you actually look at the time per linear solve, it is also quite flat. In general, we have a setup time and a solve time. And so we look at both of those because they have different characteristics to their algorithms and therefore different performance characteristics. But in both cases, we see quite flat times and very good. And so all of a sudden, we're in a regime where we can solve problems with hundreds of millions of degrees of freedom quite handily on our supercomputing systems. And these are not, we're using large numbers of cores, but given an X-scale platform, these would actually be pretty trivial problems on a system like that. I only want to show 2 examples. We've applied this method to a variety of other physics, compositional reservoir simulation with complicated well models. We're working right now on thermal behavior and so forth. Again, there's a lot of tuning and you need to come up with a recipe for your specific physics, but we find the general framework is extremely flexible. And what's nice too is it's very shareable. And so in fact, this multi-grid reduction preconditioner is available open source today in the latest release of Hyper. So Hyper is a scalable solver package, of algebraic multi-grid primarily package developed at Lawrence Livermore. And so this preconditioner is there. Now, to set it up, again, you need the recipe, and we would be happy to work with folks on exactly how to make choices about restriction and interpolation for the particular problem that you're looking at. Similarly, if you're interested in some of the physics that we've been working on, we've been developing an open source reservoir simulator, which we call GeoSX, which is really targeted at scalable multiphysics. I know there are a variety of open source simulators out there, and they're all very good. And so we get this question, oh, why yet another simulator? What is the purpose? And the purpose here is we're trying to fill two very specific niches. One is this work has a very heavy focus on seamless geomechanics. We want to make sure that in reservoir simulation, geomechanics is not an afterthought, but it's actually sort of put up front and baked into all of the solver and algorithms and mesh data structures and so forth. And then the second one is we're interested in scalable and, in fact, next generation platforms. And so there's a heavy emphasis, for example, on making sure most of our kernels can run on GPUs and our data structures are portable and well suited to new exascale architectures and so forth. So if you're interested, please check them out. And if you're interested in collaboration, let us know, and we can start a conversation around that. Okay, so I want to wrap up because time is getting on. I focused on one very specific bottleneck, but in reality, like I said, there's no shortage of problems to work on in nonlinear solvers, discretization methods, GPU programming, and portability models. There really is a ton of work, and so no lack of opportunity for good collaboration. So the last thing I wanted to close with is sort of a we're talking about high performance computing. What will geomechanics look like 10 years from now? And so I wanted to leave you a little bit with our vision of what computational geomechanics might look like 10 years from now. And these are, our work proceeds one paper at a time. It proceeds incrementally, but we do want to have sort of a coherent vision about how each of those papers, each of those projects is pushing us in a certain direction. So our first goal is really around impact. We want to make sure that the work we're doing supports, a safe, secure, and in particular, an environmentally sustainable energy economy. And so, a lot of work on carbon sequestration, geothermal energy, hydrogen storage, really thinking about what the energy mix of the future really looks like. Then I think I've hit the, really sounded this note about performance. We want to make sure that we are keeping pace with new hardware, which is opening up the possibility of all sorts of new computational paradigms, ensemble computing, GPU computing, but it also really is forcing us to rethink how we design our software. The things that work 10 years from now are not going to work 10 years. The things that worked 10 years ago will not work 10 years from now. We also want to improve the fidelity of what's being used in practical simulations, so that complicated fluid flow, thermal, geomechanical, fracturing, fault reactivation, all of these processes can be handled kind of in a seamless manner. We can do that today, and many people on this call I know work on this process, but it's often a little clunky. It doesn't scale well. We may have to couple multiple codes to do it well. And so we really want to be able to do this in the way that an engineer on a real operation could use this in a seamless way. And then the last goal is flexibility. Today, a lot of our workflows are very structured. They rely on corner point grids, which have a very structured topology. And that can become, though, very difficult when we want to do, for example, fault reactivation or fractures that somehow don't align with our grid. And so how do we create numerical seams that are flexible with respect to these very complicated geometric topologies that we need to face in the subsurface? So in closing, I would like to thank many collaborators who've participated in this work that I've shown. There's a long list here. If anyone here in the audience doesn't see your name on this list, we should write a proposal together. Let's collaborate. I believe the best science is collaborative science, and maybe we can add your name to the list here. I'd also like to thank the U.S. Department of Energy and Total, who've actually provided the bulk of the funding for this recent work. And with that, I'm happy to take any questions or discussion or comments from the audience about thoughts for the future.
Thank you very much, Josh, for this very interesting talk. I see quite some questions already being posted. More should come also soon. So I would just hand over to Sebastian for the rest of the session today.
Yes, thank you very much for a really interesting talk, Josh. And with the future, with computational power becoming much cheaper every day or every year, it's fantastic to see how we can harness that resource more effectively for work. So lots and lots of questions are coming in, and please continue asking your questions in the chat room. So the first one is from Sarah, who asks, can you further explain, please, what smoothers are? What smoothers are most efficient for each stages of UPS, PS, and P? Last one, IEP, Audi is a major field of research within algebraic multigrid, AMS, etc.
That is an excellent question. And this is one of the major distinctions between, for example, what's going on in multigrid reduction and a sort of a pure AMG applied to a single physics problem like the pressure system. So in typical algebraic multigrid, what we do is we use relatively simple smoothers, so things like Jacobi, Gauss-Seidel, which as single level schemes are ineffective as preconditioners. But by using a multigrid hierarchy, we can make those simple preconditioners scalable and effective. Okay. And so, for example, for this P system, when we get to it, we will apply some sort of scalar AMG method to it, And so here we used, a Gauss-Seidel smoother. Let me put it this way. What's complicated about this is that there is a nested level of AMG hierarchies. Here we have this field-wise reduction, which creates one hierarchy of sort of problems. But then once I get, for example, to this pressure problem, this is not the coarse grid. I can't solve this directly. I actually have to apply an AMG method to this pressure system itself. And so in some sense, there's an AMG cycle embedded in this hierarchy. Similarly, when you, for example, on the fine level, we have to deal with the displacement field. So we have to deal with an elasticity system. So again, we can't use a simple smoother. For us, a smoother is in fact another AMG call to an AMG method specifically for the displacement components of that problem. And so, so the question I think hits the nail on the head. I have glossed over a huge number of details about how this actually works. And I would really point you to the papers, or if you'd like to have a conversation, these details are critical to the success of the method. That is very clear.
Thank you. There's a question on a similar line from Yuan Wang, and he asks, thank you for the interesting talk. How would you couple the UPS reduction strategy with multigrid, multiscale in space and time?
So that's it's an interesting question. So for those who are not familiar, there is a lot of interest in what are called multi-time algorithms broadly, where at any given call to let's say the linear solver, I'm not solving for the configuration of the system at one time step. I may actually be solving for the configuration of the system at several time steps at once. And so what you can imagine that I might have the displacement field at time n+1, n+2, n+3, and I solve for them all sort of simultaneously. And the reason for doing that is that there's some argument it can create a lot of computation intensity, in the sense that we can do a lot of work without a lot of data motion. And so there's a lot of sort of interest in these types of multi-time methods. Specifically to the question, I think you could do it. There would really be two ways to do it. The first would be, and it depends on the ordering of how you do the reduction. In this hierarchy I've shown, this USP system could actually be, I suppose, a multi-time system, that it would actually represent the state at multiple time levels, right? Alternatively, you may have some sort of reduction where you kind of do the reverse, where the time reduction is actually at the outer level, and then at any individual time step, there is some sort of inner reduction. I am, of course, thinking out loud here. It'd be interesting to talk with you about the specifics of what this might look like. I certainly don't see any intrinsic problem. Again, it's just a question of reduction order, maintaining sparsity in your system, the classic things that we want to do in AMG. Maintaining operators that are well suited to the smoothers that we use, and so forth.
Thank you. So plenty of questions. Just trying to see how we continue in the best way we continue. Where was just trying to find the one that I picked out before. Yeah, because we started talking about solvers. So Timo Garipov asked, does the linear solver require modifications for different approximation techniques such as finite volumes, pneumatics, etc.? Does it work out of the box?
Right. Excellent question. Yeah, I don't. So first of all, let me take a step back and be very clear, because this is an algebraic solver in the sense that it needs very limited information from your reservoir simulator. Really, we work just with the matrix itself. We do, for example, need to know which rows correspond to displacements and saturations or whatever the physics is. That's what we need from you, is to say this unknown is actually a temperature unknown. Okay, so that's it. But it is also like algebraic multigrid in the sense that it is not a true black box. It's a little bit more like a gray box. I can take an algebraic multigrid method with a really poor choice of restriction and interpolation and really poor smoothers for my problem, and it will work terribly. And vice versa, with a good understanding of my physics, I can choose those settings in such a way that it works really well. And so that's what we have here, is that we are recycling very similar tools, but you do have to make some choices that are very problem specific. Okay. So now to the more specific question about, does it work out of the box, for example, for a mimetic method? And the answer is no, because, for example, imagine that, imagine we come to this P system, and this P system has been discretized using a finite volume scheme with cell-centered variables, okay? So that's the type of thing that we could directly apply AMG to, a scalar AMG to. In a mimetic scheme, you may have cell-centered pressure variables, but also face-centered pressure variables, okay? And so now we may, for example, want, that system intrinsically is not particularly well suited probably to scalar AMG. And so we probably want to do a further reduction. So for example, eliminate the cell-centered pressure variables onto the face stencil, and then make that our coarse grid solve. And so yes, it won't work out of the box, but we can configure it to work. And I will say very concretely, we have actually done this for mimetic flow discretizations. We actually use MGR for mimetic methods. So we have a different recipe. It's not the recipe that we use for a TPFA finite volume scheme, but it is a recipe that works. I will say my colleague Francois Hamon has been very heavily working on mimetic methods, and he's been actually leading the charge on this. And so Timur, you obviously know Francois, I would get in touch. I think there's lots of good opportunities for discussion there.
Thank you. So just staying on the discretization side for another moment, Yang Wang has a second question, wonders, could you comment please on the use of structured, unstructured grids in terms of accuracy and computational efficiency?
Well, in general, it is true that if there's any sort of structure to your topology, you can exploit that to create a more computationally efficient algorithm. The challenge for us, I think what we see is that, well, okay, so let's just take that as a given. I think if you told me that there was some inherent structure, I could exploit it probably. What that means though, there's a variety of levels of structure. There are Cartesian grids, which is kind of like one level of structure. There's a corner point grid, which is structured in the sense of an IJK logic, but if you actually look at the topology you get, and particularly like the face connection topology, there can be no structure. You could have degenerate elements, all sorts of stuff. There is fully unstructured sort of finite element type meshes. That would be kind of one extreme. And then there are, like an unstructured coarse mesh, but where I do structured refinement within blocks. And so I think anytime there is structure, we can take advantage of it. So I always start with the question is, I think the first consideration is, do we need unstructuredness? And so for some classes of geomechanics problems, it's very clear that we do need unstructuredness. I can't do fault slip reactivation on a corner point grid if I've got like stair stepping. It's very difficult to do. I'm immediately going to caveat that, but you imagine using a standard coordinate grid and sort of standard methods. I need a conforming discretization. I'm already talking about an unstructured grid at that point. So now here comes the caveat. There is a whole field of research of saying, can we use structured grids and enhanced discretizations to represent unstructuredness or physics in a non-conforming way, physics that doesn't conform to the grid that we use. And so, for example, extended finite elements, embedded discrete fracture models, the idea, can we embed fractures that cut across our grid in arbitrary orientations and sort of free the physics from the grid? I don't know anyone who's worked on it, but I imagine that you could take a corner point grid and an XFEM or similar type embedded discretization scheme to come up with a logically conforming an unconforming representation of a smooth surface and do fault reactivation. So maybe someone's already done it. So, but yeah, I mean, in general, we do try to exploit structuredness. It helps a lot. We want data locality, we want data density, we want simplicity of algorithms. But at some point, you have to give up on that for flexibility in your physics.
Since Rainer Helmich, one of our previous speakers, once told me, you're always going to die one death when you try to do numerical discretization. Yep. There's always one problem that you need to, the less bitter pill that you need to decide which is the less bitter pill that you're going to swallow. There are a couple of questions around your code, and they're very similar, so I'm reading them one after the other. So the first one is from Musa. Very nice talk, Joshua. Have you benchmarked your simulator? If yes, how and what problems? How convenient is it to work with? And Kishan has a very similar question. Is your simulator benchmarked with lab field scale data or any existing simulator? Very curious to know about it.
Okay. Well, so again, context is important. So we've been working on this simulator for about 2 years, and we've just made it open source. And it's targeting a very particular, well, a few particular niches, like I said. And so there was a very nice seminar in this series a few times ago by Knut Andreas Lee talking about the MATLAB reservoir simulation toolbox, which I think is an amazing project. We use that all the time. When we want to prototype algorithms, we use MATLAB, we use MRST. When we want to benchmark against it, it's really great. And so I would sort of put that one at the one end. It's really about flexibility, ease of development. I think Knut Andreas made a nice argument, though. Even MATLAB hooked up to a good linear solver can actually solve like quite substantial problems. Okay, so that's kind of one end of the spectrum. We are sort of at the other end of the spectrum, where we have a very complicated programming model in order to enable portable performance on a variety of different architectures. So various GPU systems, CPU systems. We have kind of hybrid parallelism where you've got MPI and OpenMP type threading, or GPU sort of threads running in parallel. And so it's written in C++, but then on top of it, it's got this portable programming paradigm. So is it easy to develop in? We do our best to make it easy to develop in. We want people, we try to modularize it. It's written in a very modular way. We spend a lot of time on documentation and tutorials. We have graduate students working in the code, putting their algorithms in there. And so, yes, we think it's easy to work with. Is it as easy to work with as MRST? Not by a long shot. To work in our code, you do need to kind of understand C++. With time, you'll need to understand Raja, which is our portable programming model, and so forth. But we try to modularize that. So if you're interested in developing it, the first question I would ask is, what is your goal? If your goal is to say, I have an algorithm, I want to try running it on a big problem. I want to run it on, maybe 1 million grid block reservoir mesh, and then maybe 100 million, and then maybe I want to be that person who runs it on a gigagrid, this is where you probably want to be. Like, we want to support that sort of large scale. If you just want to sort of prototype an algorithm, you probably want to do what we do, where we start with MATLAB to really understand the importance, the structure, the algorithm itself, and then we start porting it into our big toolkit. Then there's the question about users of the code. So we support certain problem classes, compositional reservoir simulation, some types of geomechanics. We're actively developing new physics, so I don't want to imply that, oh, we've solved everything. In that 10-year vision, it really is a 10-year vision because we think it will take us 10 years to get there. But we do a careful job with what we call our continuous integration. We run benchmark problems. We compare with analytical solutions, other reservoir simulators. So we do our best to compare against existing codes. But like any big code, it's got bugs. And so as people use it, post a bug, we're very responsive. We fix it. We want to find out about bugs. Invariably, someone wants to use it in a way that we haven't thought about. And that's good. And so we rethink our algorithms to be a little bit more flexible and so forth.
Thank you. So we're sort of running out of time, but there's one somewhat philosophical questions to close with, which is, I think, is a really nice question. So again, so two-part. It starts with a comment from Dan Rees. He says, very interesting talk. Thank you much. It's impressive to see how such big systems can be solved. Then his questions, and I think that's a really good question. Do you do any research on reducing the system by prioritizing features in the subset that have greater influence on flow with respect to features that have less influence? So rather than just going on bigger on computer, can reduce the system to focus on the physics that really matter and solve them as efficiently as possible, and perhaps smaller grids or more tailor-made grids.
Great. This is an excellent question. Because it is a kind of a philosophical or thinking about the future. For the past 10 years, every time we got a new machine, the mindset has been, let's run a single realization of the problem on a more refined mesh. Let's just run, bigger and bigger problems. We thought about heroic calculations, and there is certain physics for which the next generation of machines, that every time you run a bigger and bigger problem, it does add new insight. So in geophysical imaging, for example, the finer your mesh, the higher frequency content you can put in there. And so you can say the bigger problem I can run, the more I'm going to understand my system. Okay. But for reservoir simulation, I can see real value in making a reservoir model with 1 billion grid cells useful. 1 billion, there might be situations where you want to make that kind of like, oh, we can handle that in day to day. But are we going to learn more from having 100 billion grid cell model? Or are we going to learn more from having a single realization of a reservoir with 1 trillion blocks and the rock discretized down to a centimeter? And the answer is no, because we're going to be overwhelmed by geologic uncertainty. And so when you look at these big exascale machines, we think about, well, how are those actually going to be used in practice? Is someone going to solve a single realization on that whole machine? Or I think in many of our workflows, what we're really going to be doing is ensemble computation. We will have running in parallel smaller models, each of which doesn't take up the whole machine, but is being run in sort of an ensemble fashion to do something. Maybe it's doing uncertainty quantification, maybe it's doing machine learning. We're building reduced order models for the system and dynamically launching realizations and shutting down other realizations when our machine learned model can adequately represent the physics. We have to take a much more flexible mindset to the future of computation. And so to this specific question about, this is really a question about uncertainty quantification, and so we want to do, for example, sensitivity analysis. Maybe we run some sort of hypercube type sampling. We run lots of realizations of the models. We discover, for example, that the overburdened bulk modulus really just doesn't impact the results for some reason. We can actually then remove that from our uncertainty quantification. We could remove that element from our physics maybe. And continue in that way. And so, yes, I think that will be central to the future of computing, is using these large resources to really understand sensitivities, uncertainties, risks, these sorts of questions.
Thank you very much, Josh, and thank you to all the attendees for asking plenty of questions. Apologies that I can't go through all of them. We're already well out of time. But I didn't want to shut down really interesting questions and insightful questions. So thank you to the audience. Thank you to you, Josh, for all your talk, for your insightful answers. And back to you, Hadi.
Thank you very much. Thanks a lot to the audience also from my side. I would like to quickly announce the next speaker. We are going to stay in California. So we will be hosting next week Professor Jeff Kears from Stanford University. Jeff will speak about Bayesian evidential learning, a scientific protocol for uncertainty quantification. And that was the last point that Josh also mentioned. So it's going to be addressed quite extensively next week by Jeff. Until next week, everybody, please stay happy, healthy, safe, and tuned. And we are going to see you next week at the same time again. So thanks a lot, Josh. Have a nice day. You started the day quite early, and we are closing the day in Europe. So stay well. Thank you, everyone.
Keep waking up the people on the West Coast. Thank you, everyone. Bye-bye. Thank you, Josh.